Hello, my name is Sean Anklon, and this is my final project for uh, photovoltaic energy conversion EEE 465 spring semester 2022. So introducing my technical problem, for this project, I'm going to be comparing the existing photovoltaic system that is currently installed at my house with a system that I will design. Key differences that uh, will exist between the two systems are grid connection and batteries. The system I'm designing will be off the grid and will have a premium battery as opposed to maybe a lower quality one. The goal of my analysis is to see the differences of cost, availability, and efficiency. Some critical technical problems are definitely lowering the cost of my system while increasing the performance compared to the system at my house. Seeing how the system changes um, as an off the grid system rather than being on the grid, and checking how the cost affects availability. So some background information. The goal of my project is to create and test a photovoltaic system that will be compared against obviously the system installed at my house, seeing the difference between the costs of the two systems. One might be more expensive, one might be less expensive, and finding out how available these systems are for lower income earners. Maybe people who make less than 50K a year. Some equations and formulas I'm going to use is the various equations used in the shell code of projects 2, 3, and 4. For example, the efficiency equation from project 2 will be used. I'm using all the financial functions, including the initial cost function, the NPV function, and the annualized cost function. I will also be using the electricity rate and heat map functions for the plots. For the previous relevant work that I'm using in this project is the shell code from mini projects 2, 3, and 4. I'm using module and array information for my house. Like I'm also using load information and energy creation from the PV system for my house. And I'm also using load data from the power company versus calculated load. How is this different from other work? This is different from the other many projects in this class because it's incorporating knowledge into a personal project. It's different from other work done in photovoltaics because instead of just installing one system, I'm installing one system and comparing it to another system and trying to see which one's better. And it's different from work in my other classes because it's a project with a lot of creative freedom. I could do whatever I wanted with this project. So I decided to compare a created system with a pre-existing system. As for technical approach, my approach was to use the filled out shell code and data from my house. I came up with different figures to determine which system is better. Some criteria I came up with is the system that's cheaper, more available, and more efficient will win for the better system. The program structure is just all the shell code from many projects 2, 3, and 4, as well as the financial functions that were provided for this project, like the NPV functions and the initial cost and annual cost. Here's some of the parameters I chose to use in the shell codes. I decided to go with a doping of 1 times 10 to the 19 per centimeter cubed and a thickness of 0.5 times 10 to the -4 centimeters, because that gave me the highest efficiency if I was to like develop the modules myself. As for the shellcode for projects 3 and 4, I decided to go with 300 watts per module. The number of series is 12, and I'm having 2 number of module series. And the rest of those, I tried to keep it as close as I could to the system at my house because I didn't want to cheat and just give it better values. Here's the parameters I selected for the financial code. The system wattage is 7,200 because there's 24 modules at 300 watts each. The capacity is 13.5 kilowatt hours. And the voltage is 960 because it's 24 modules in parallel at 40 volts each. And yeah, there's 24 modules. Also, I selected a Tesla battery for my system, which is $8,500, which is more of a premium battery than the one at my house. Here's the data from my house for comparison. The load is at the top. Obviously, the months of May and June are a lot higher because that's when we start using the AC here. All the winter months of like December and January, it actually, the load is negative from how much we don't like use any electricity. And then there's the energy produced at the bottom from the photovoltaic system currently installed at my house. It creates about 9 megawatts per year. And I mean, we've had it for, I think, 5 years. So it's created 47 megawatts so far. Here's my system. The figure I created for the load for this standalone system would be around 650 kilowatt hours, which is average for a Western home. And I actually added a little more because it's off the grid. The photovoltaic energy generation is on the right, and it's around 1 megawatt per month, which completely covers the load, and it probably takes some stress off the people living at the off the grid system. Here's more results and analysis. The cost of the system. The 2 heat maps are on the left, like the rates in cents per kilowatt hour and the electrical usage per hour and like money per hour. And then the top right graph is the usage rates. Like they go up in the summer because more people are using it, like AC. Here's the figure. The figures are on the bottom. The monthly charge of my system would be like $389, and the usage would be -426, which would mean the electricity company would pay the users of the system $37 a month. The initial cost of the system is $8,496. And that figure isn't totally accurate because you'd have to add the battery, which is $8,500. So the system would be about $17,000. The net present value would be $21,000. And the annualized cost would be $1,200. The relevance to the technical problem These results are relevant because they prove my system is more economical and available than the current system currently installed in my house. Uh, it's 17,000 versus 18,500. Like even with the added cost of the battery, the design system is still cheaper than the pre-existing system at my house. This means that living off the grid is possible because the surplus of energy is created every month and stored in the battery from the PV modules. So how does this impact a broader context? This project impacts broader context because it shows that PV is more accessible to lower income families and households. With a cheaper battery, the system can be installed for maybe even less than $10,000 in some case, which could be worth it for different demographics. And last point, cheaper systems means more systems will be installed throughout America and the world, and that will make for a cleaner environment and climate. One more slide, why my solution is the best one. From the figures provided, my modules are higher efficiency, 22%, and the modules at my house are only 17%. The initial cost of the system is much lower. It's actually 17,000 versus 18,500. This is due to different factors, like the system at my house uses microinverters versus a large inverter, and the decreasing cost of photovoltaics in general. And the system is more available to a broader customer base because of the cheaper price.